So let me start again by thanking the organizers and especially the advisory board committee for this opportunity to speak again. So I'm going to speak today about QQ bar potential. So I didn't know how to do bar, but it's about QQ bar. And if I have time, I will speak about some other more recent results. So I'm going to describe. Okay, people are still coming. Maybe I wait a couple of minutes. It's always a problem. The last time I also spoke after the lunch, and I had to repeat all my jokes again. Huh?
Could you repeat the joke?
No, but now it's different, right? So you will have, unfortunately, to see the jokes in the recording. So recording will be available on soon, I hope, right, on the web page. So I'm speaking about QQ bar, and I'm going to describe a closed system of equations for this absorbable, which was studied intensively, perturbatively in the past, and also integrability results were available, and then now I will culminate this development with quantum spectral curve formulation, and which allows for numerical and analytical studies of this absorbable in the nicest possible way. We'll see. So before I begin, I will start by describing the quantum spectral curve for the local operators in the cleanest possible way, which the way we understood it now, which is very simple. So, but before I have to, okay. So if we just take the simplest integrable model like XXX spin chain, which is also, is a weak coupling limit of our beloved n equals 4 super-Young-Mills in some sector, then we can describe it in terms of the Baxter equation. And Baxter equation is like a second-order finite difference equation. It must have two independent solutions. And it's nice that both the solutions, even only one is needed to construct the bit ansatz. The second solution also plays an important role because I can replace completely the Baxter formulation by just a simple determinant of these Q functions, and with a statement that this determinant is equal to some fixed function u to the L, which can also be interpreted as a Q function. And then this equation actually completely replaces the initial Baxter, and if you require that there are such two polynomials Q1 and Q2, which satisfy this equality, it's equivalent to the Baxter equation. You'll find all the physical states of the XXX spin chain in this way and compute the energy and all other consort quantities. And what's nice about this formulation is that whereas the Baxter equation for SU3 is quite involved, and there are two actual equations, or depending on how you formulate it, its generalization in terms of the Q function is very simple. You just extend this determinant to be 3 by 3. You just change the shifts a little bit, and you get exactly the same formulation in terms of Q function, which is equivalent to the quantization. So it will give you the discrete spectrum of such polynomials, each corresponding to some state of the theorem. Okay. Oops. Okay, and that's this formulation which we take with us because it's so nice and universal. So the only thing we have to do, we have to just replace. So in my case, SU2, I forgot to change, to PSU2, 2/4, so which allowed just replacing two Qs by 4 plus 4. So like 4 living in S5 and 4 in ADS5, describing 4 plus 4 degrees of freedom, bosonic degrees of freedom. Because that's just that. So wait, let me do this one. Yeah, this one, it becomes quite bulky and it's ugly. I don't remember it by heart, whereas this I can easily reproduce. Yeah, and there are two equations, you don't know which one to choose and so on, whereas this one is unique and the nicest possible. Also, it reflects the symmetry with respect to the arbitrariness of choosing different vacua in the theory and so on. So it's like the nicest and most natural way of doing that. What we have to do for our n equals 4, we have to just take exactly the same QQ relations and just extend the number of Q functions and like do some superdeterminant at some point or some analog of that with shifts. So it's some quantum superdeterminant or whatever replaces it. The question is, however, so before it was important that both Q's were polynomials, that what actually made it the discrete the spectrum. So the quantization also contains the analyticity conditions on the Q function. So the question is, what is the analyticity conditions on our 4+4 Q functions? And to get some idea, we can turn to the strong coupling formulation, which is given in terms of the monodromy matrix, as we know. So I don't repeat all the details, but if you like write the monodromy matrix, which is a function of like tau and the spectral parameter u, if you write it in the most natural spectral parameter, which is consistent with WKB quantization, so there is only one such choice, then you'll find that actually no matter which state you take, you'll always find the cursor, and then you find the cut. So this cut from -2g plus g will be present for any state. And the question is, what happens, like, what the gluing conditions for this cut? Okay, and some of you may still remember that the gluing condition, it takes this form, so you have to conjugate your monodromy matrix with some constant matrix, and also invert it and super transpose it. So which in the language of the eigenvalues, so eigenvalues of monodromy matrix, so it's hard somehow to trace it. So eigenvalues of the monodromy matrix again 4+4, and then this just means that we have to flip the sign of the eigenvalues when we go to the next sheet under this cut, and also maybe reshuffle them in some way because of this constant matrix C. Okay, so that's what we find. You can check this on some solutions to check the precise coefficients. Okay, so these are the gluing conditions. So now we can try to extend these gluing conditions to the Q functions. And we can do it just because there is a simple relation between this P and Qs and the quasi-momenta, the eigenvalues of the monodromy matrix, namely it's like WKB quantization. So P plays role of the classical momenta of like one-dimensional particle, and then P is just the exponent of integral of P and Q. So this is the identification of strong coupling of these P's and Q's, which you can check like for the XXX spin change, for example. Okay, so what we have to do, we have to now write some gluing conditions, analog of this Q tilde B and minus Q for this capital Q's and P's, maybe. So, but the problem is that it will flip the sign, and so there will be no nice like linear identity. But this is resolved if we realize that actually the PSU 2,2/4 has the following symmetry. So we can rotate it, and so there are two natural bases in the Q functions. One can be identified like one can denote it with upper indices, another with lower, and they're like related by some Hodge transformation. But otherwise, they should be equally nice. So upper and lower, they're just a reflection of this symmetry of PSU 2,2/4. And now you don't have this problem, and we can just deduce that this relation implies that Q1 tilde should be, say, Q2 bar with upper index, and so on. So this just follows exactly the pattern of the classical string. And I have to add the bar. That is something you can't see classically, but it's become clear when you analyze analytic properties of Qs and Q2. So there is another symmetry that you can conjugate because the series is unitary, right? So you can. What we have to do is to combine both symmetries, flipping symmetry and complex conjugation, and then this will give you the kind of isomorphism equivalent to the analytic continuation. So when you go to another cut, what you find is the same system, just complex conjugate and a bit reshuffled. That's the message, okay? So it's very simple, and that's all you need to start solving it. So now we can take this simple idea and build a universal computational scheme out of that. So what we do, we start from P lower and P upper, and we use this as our basis. So it's enough to take these two functions to be able to reconstruct all Q functions. And then, so they have just this one cut, which I mentioned before. And so they can be parameterized in terms of these Zhukovsky variables. I just do a Taylor expansion in 1 over x. Okay, it's regular at infinity, because at infinity its behavior is under control. It contains just as 5 charges. And after that, you just Taylor expand around infinity in this Zhukovsky variable. So this is nice because this on that, it gives, so once you specify C, it will give you P everywhere on the upper sheet and slightly below. So it goes on the next sheet as well. And so you can also get P tilde, which is the analytic continuation of P, inside this, in this oval. Okay. And the message is that now these coefficients, they're like analogs of beta roots, so they completely determine the wave function of our state. So before it was enough to specify the beta roots to build the Q function, which is a wave function. And now we just have to specify the C's, and that's an equivalent description of our wave function. So it contains complete information about the state. Okay, so, but we have to now find the way to constrain these coefficients. So far they are arbitrary, and for that we have to use somehow the gluing condition. And gluing condition is written in terms of Q's. So for that we have to reconstruct Qi. So and for that we only need to know one single QQ relation. So this is one of those relations I showed you in the beginning for the XXX spin chain, just written in a bit different way. So we just need to use this identity, and since P's are fixed, we can find this Q with 2 indices. So why do we care about this Q with 2 indices? Because this is like a rotation matrix from like ADS5 to from S5 to ADS5. So it actually has some orthogonality properties and so on. But the way we use it, we just contract this index A with A of P, and we get immediately Q. Okay, so this Q we determine out of this equation, which is completely determined by P, and then we find Q and Q tilde. And then, okay, so some comments. And then if we know Q and Q tilde, we can now apply the gluing conditions to fix the coefficients. So, but let me say a few words how we solve this equation. So you see this equation, okay, come here. So this equation, it relates Q with minus I over 2 with Q plus I over 2. So you can like express Q of U in terms of Q, where you shift argument as much as you want to the upper half plane. So this, and then you get the structure which looks like some kind of monodromy, or I don't know, path order at exponent, which like shifts the argument of U. So if you fix somehow Q at infinity, you will reconstruct the Q of U if you know P's. And P's are fixed. So how do we actually compute this infinite product? This is like similar to infinite sum. So how do we compute infinite sum? That's very easy if you know a special expansion of the function you want to sum at infinity. So say you have first reorders at infinity. Then you can add and subtract the asymptotics from Fn and truncate the difference at like first 10 orders, and then it will already give you the sum with 10-digit precision just by computing a sum of 10 terms and adding a few zeta functions. So and then this is how we do this product of Q of 1 plus P's. So in this way we reconstruct QAI in terms of coefficient C's, then we find QI just by rotation, and then we impose that QI tilde should be QJ bar, and this gives an equation for C. And then actually we observed that only half of these gluing conditions are needed somehow, but it's purely experimental fact at the moment, so there's no proof of that. And then you can solve this constraint on C by just a simple Newton method, which like gives you results in a few seconds. So you can see actually the code which reproduces this result on the Rezush Summer School web page, if it's not removed yet. Hopefully it's still there. Maybe you can ask Volker, who is always happy to help if you have problems. And this code was also like implemented in C++ just to improve the precision.
Not Volker, but Fedor.
Fedor? Would Fedor know? Okay. No, Volker will send you to Fedor probably, that's what will happen. Okay, so this was the story for the local operators. Now my mission is very simple. I just have to tell what changes for the quark-antiquark potential, or more precisely, for the cusp Wilson line. So it's now non-local operator. You have like a Wilson line and with some cusp, and each part of it is like BPS. So that's only non-trivial when you have the cusp. Phi and theta, the angle in S5. And also as a parameter you have lambda, the Toft coupling obviously, right? So we want to compute this quantity as a function of these three parameters. Okay, so let me just list the modifications required. So these modifications, they should include these three parameters into the game. So what happens is like phi and theta are very easy. Okay, go up, go up, go up. Very easy to implement. We just add this twist to q's and twist to p's. So now these angles phi and theta, they are very simply the exponents of this p and q. So before it was a power like for local operators. And it's also the same actually for the case Volodya considered for this beta, gamma, and so on deformed series. And then delta appears here, and that's more or less it. And there are some modifications which are roughly speaking due to the boundary. So we expect some effects from the boundary scattering matrix to appear. And the only effect is that like each p and q, they have a half zero at the origin, roughly speaking. So basically you, p is some function times square root of u, what I mean. So p squared will always contain the zero, which corresponds, at the end of the day, you can trace it back to this periodic structure inside the boundary scattering matrix. Okay, and then also the gluing conditions, they now got this cinch. And the cinch, I should say, is like always appears whenever you consider some non-local type of operator. But actually, again, only half of the gluing conditions is needed. And I just will use this first equation here, which is just the usual gluing condition, like for the local operators. Okay, and then we just, the way we got this, so of course, like it was back and forth, like inverse engineering and all these messy techniques, which are impossible to describe on the talk. But after 2 years of struggle, we fixed all these modifications required to match with some known data. Okay, so otherwise everything is the same. You can do numerics and study it in various ways. But what is actually challenging, both technically and also interesting from the physics perspective, is the so-called flat space limit. So this, I think, was introduced by Nadav and Valentina. So if you take this limit when phi goes to pi, then basically what happens, if you look at this picture on the cylinder, these two lines, they come close to each other, and in practice it means that there is no effect from the curvature of this cylinder. So what you are doing in this way, you are computing an expectation value of two antiparallel Wilson lines, which naturally correspond to quark-antiquark potential between two very heavy particles. Okay, and so what happens in this limit when phi goes to pi is actually, of course, you should observe the Coulomb potential, which is the difference between phi and pi, which becomes a distance on the cylinder. Oh my gosh. And then omega is what we want, is a non-trivial function which we want to find. Okie dokie. Okay, so however, you can like expect that something funny happens in this limit. So with we would like to write some closed system of equations rather than like dealing with phi finite and then sending phi to pi each time. So we want a finite set of equations, but this delta becomes infinite, and delta appears in the asymptotics of Q, and that's very crucial for us because we have to select exactly Q1 and glue it exactly with Q3, right? If you do some Q1 plus Q2 and glue it with some Rebish combination, it won't work. That's what's important, is to select the precise Q functions and before you glue them. So we have to identify what happens with the asymptotic of Q in this limit. So unlike some kind of argument which oh la la, what happened? Zurück, no. Okay. So kaput. Yeah? Okay, now it works again. Okay, so we introduce this epsilon, which is like distance from pi. And then you see that this delta becomes infinite, and it becomes very large. And I can like put it in the exponent, so it will multiply log of u. And the twist will introduce this u times epsilon term. And then somehow I want to deduce what will happen when epsilon will go to 0. So I should probably say that actually I borrowed all the slides from further. So this is why here there is a mistake, unfortunately. So it should be 1. That should be 1 over square root of u further. You should finally fix it. Okay? So where am I? Okay. So you see that these two terms, they balance roughly when epsilon is order of square root of u. And then what you'll find, okay, log is not a function, right? Everyone knows it's just a constant. And then what you'll find, some constant times square root of u. So what we expect is that in this limit actually we'll find some new type of asymptotics, which is not typical for any other situation. Okay. And then the scientific way of doing that is actually to observe that nothing special happens to P, because P lives in S5 part and it doesn't really care whatever you do with angles and like very remote ADS part. So phi is completely finite and it's not nervous about this limit at all. So you just take your P and you find an equation for Qi again, and this will give you the scientific way of fixing this constant in particular, which you'll find is related to this omega. So this constant C, which we found from this strange argument, is actually omega, what we want. This is the Coulomb, the charge of this quarks, if you want, square. So actually it's square root of omega, so it's just charge. It's funny. Okay, so this is completely kind of a surprising type of asymptotics, which we've never seen in spin chain somehow. And now we have like a closed system of equations. We have this square root of u at infinity multiplying omega, and then all the rest is the standard quantum spectral curve. So the scheme is the standard one. We just build P in terms of some coefficients. We call them now A instead of C, I don't know why, and then we find the gluing conditions, and for that we have to identify Q1, and Q1 is the one with minus square root of u at infinity, because there is also this plus square root at infinity, and this garbage we don't need. We just need one Q in this game, which corresponds to Q1. So it's the smallest solution in a sense. And then from matching from requirement that Q1 tilde is Q1 of minus u, which is the same as Q2 with lower index, or Q3 with upper, we find omega. Okay, and then you can do numerics and so on. I will show some data. But what is interesting is the weak coupling somehow limit, because it's kind of contains a new type of structure. So at weak coupling, if you observe a known results, you'll see that actually the limit of lambda to 0 and phi to pi, they do not really commute in a sense. So there should be some reference to Nadav. I think he is already nervous. Okay, I hope it will appear later. Sorry. Okay. Okay, at the leading order, you see it's the same. And at the next order, you'll find a log of pi minus phi instead of log lambda. And you see that actually for this quark-antiquark potential, there is this log of lambda appearing, so it's not like a usual perturbation theory. In a sense, it's also perturbation theory with logs. Okay, so this matches and it doesn't. So the question is, how could it be that in the usual perturbation theory we encounter this log of lambda? And actually, the way it happens in n equals 4 is that you have to really do a supermassive computation. You have to take into account some infrared degrees of freedom. So at the end, you have to deal with some effective field theory. So good luck with that. But at the same time, it's also quite challenging from the quantum spectral curve. But we found a way to deal with that efficiently. So let me say how it happens at this level. So if you take your quantum spectral curve and just naively expand in G, you'll find again 4 Q functions, but in the wrong basis. And you'll find them with some just power-like asymptotics. And you don't know actually which combination of them, neither combination of them would match this e to the minus square root, remember? So at the end of the day, we have to find the combinations of q's, which at large u behaves as e to the square root of u. So none of them matches, so it's a bit strange. And we need exactly this type of Q1. So and the answer is quite natural, just omega goes to 0 as G goes to 0. So there are different scales in the game. So one scale is when U is very, very large, is much bigger than 1 over G, and that's where you actually have to expect this asymptotics, which will identify your Q1, and the Q1 is the only one you care about, right? So we don't care about any other. So Q1 is identified here. But then there is this purple intermediate domain, which is takes like a desert in between. And then a usual perturbative regime is here, the one I showed on the previous slide. So somehow we should find a way to go through this regime here, to match this asymptotics, this square root, with just power-like and logs in the middle. And then after that, we know which one exactly is Q1. And we do the gluing and find omega. Okay, so okay, there are these steps, things to further. Okay, so that's what we have to do. And for that, we have to solve our equation in this purple domain. So what happens in the purple domain, you're in a situation when U is large. So instead of finite difference equation reduces to differential equation instead. But it is still fourth order differential equation, which at the leading order have this form. Okay, so the first instinct is to put it into Mathematica and do shift enter as soon as possible. But then Mathematica, okay, solves it, but in terms of really awful functions. And so we struggle for a few days to actually realize that all the 4 solutions of this equation are all the 4 known types of the Bessel function. So it's like Bessel K, Bessel Y, Bessel I, and some J, Bessel J. Okay, so we struggled a bit with those monsters Mathematica gave, but then we realized it's just nice Bessel function. So probably this equation carries some names, so I don't know, because it's really how the Bessel function should be defined, right? So normally I define 1, then you do I to minus I. This is very boring, but here it's like all of them are. So this should be in the textbooks probably. So, and then, okay, that's exactly K1 which we need, because K1, it has the square root asymptotics, the one which is required for us. So K is Q1. So K is like Q1 friend, okay? That's the message to remember. And then if we expand K at small, argument, we'll find just powers and logs, and this exactly matches those Qs I showed you on the first slide. Okay, so however, what happens? So, okay, we were lucky to solve this equation at the leading order, so just bases, very nice, but then you want to solve, there will be, of course, some corrections to this equation, right? Then you have to like find a green function, which, okay, you know the 4 solutions, okay, bitter function is fine, but then you have green function is fine, is known, but then you have to integrate the correction to this equation with this green function. So at each order you get one integral with some ugly bases. And this is really hard to deal with, and we would probably just give up at the first order if it was the case. If not, that we observe that one can just make an ansatz for f in terms of like k, what is the cursor? K and the derivatives of k with respect to parameter 1. So if you take derivatives with respect to 1 and just make an ansatz, then magically enough, just the equation fixes this coefficient and that's it. So you don't have to deal with like a green function, all these kernels. It just solves by the magic of integrability. So it's a huge advantage. Okay, and then you just find omega, that's the most complicated part, all the rest is quite standard. Okay, so we solve this up to 7th order, which as I said would be impossible to do if not the luck with this equation which we had. And so these are a few orders here which match the known data. And then, as I said, we did up to 7, and the 7th order doesn't actually fit the screen. And if you want, you can do 9, but it's already a bit annoying because like you have to wait 1 day, and if you do a mistake, you have to fix, wait another day. So, but it's doable. So it's a systematic way of doing that. And then, as I said, this is just usual quantum spectral curve at finite coupling. You just do the usual numerical analysis. You can get lots of points with 20-digit precision. And it matches like 3 loops, which were known before, 7 loops. And also at strong couplings, there are 2 loops, so 3 level and 1 loop known. And so you can fit. That's your fit, and this is what Valentina computed. And also you do some checks at weak coupling. So it matches all the data at weak at strong coupling. So still, I mean, it probably would be interesting to get this analytically, this coefficient, but at strong coupling is still a bit a mystery how to solve analytically. Okay. So now about this, this limit which basically Volodya was speaking about on Monday. So here this limit was also known actually for some time. And out of the spider net which Volodya like made for you on Monday, we just keep one ladder, one segment of this spider net. And so this is called ladder limit in this case. So which means basically that you have to take our, we have to take our 7-loop result and kill all these terms with t's, where t's are some 1 over cosine squared theta's. Okay, so what is mysterious in this limit? There is some mystery and challenge. It's actually quite entertaining, this limit still. So the mystery is that actually at the same time it's not that you can just take diagrams, do beta salpeter equation, and you'll find a Schrodinger equation for this omega. So omega square will be will correspond to the energy spectrum of this, so to the ground state of the Schrodinger equation. And so the question is, how does it map to the quantum spectral curve? So a map is not totally trivial, actually. So at least the first step is quite simple. So you can write the Baxter equation for Q1, and you'll find that actually there is some simplification. Namely, it reduces to a 2nd order equation, which is nice because you have 2nd order Schrodinger and 2nd order finite difference. And furthermore, if you do a Mellin transform, so where is the Mellin transform? This Mellin type of transform, this Q1 will be exactly this F. So however, so still it's not like complete match, because for Q1 we still have to impose some condition at the origin So at the origin, it should glue with Q1 tilde. Whereas for f, we have to impose some condition at minus infinity. And so you would naively think that probably when u goes to 0, it tells you something about f at minus infinity. But actually, it tells you something about f at I. So we like spent a few days like with this puzzle, but then we realized that actually f, it has this equation, it has some funny property that if you do it Fourier transform of this f, you'll find the same equation, right? So which means that f, so Fourier transform of f is f itself, right? And then large asymptotic of f is controlled by the first singularity of f itself, which is at I. And then in this way, you relate the behavior of this f at I with its behavior at minus infinity, which is not immediately obvious, even if you know the map between q and f. So this was quite fun. Okay, and I said there is a link with what Volodya was saying. Okay, and just for arbitrary angles, let me mention a few analytic results. So we are now in the situation where phi and theta are arbitrary. And what we can do, we can go to this near BPS limit when phi is close to theta. At the leading order, we almost immediately recover this famous result about basis. It just follows from the Gruen conditions, basically. And at the next order, it's kind of a monster. But you see some traces of actually the Dressing phase. So namely, this gamma is nothing but very familiar from the Dressing phase combination of gamma functions. And that is a double integral exactly like in this Beider-Staudacher, hidden Beider-Staudacher Dressing phase. However, there are also some terms which are kind of twisted version. I don't know, maybe it's like Q-deformed Dressing phase. There are some specialists who should know probably. Is it Q-deformed Dressing phase or not? So when you have, instead of gamma functions, some twisted version of gamma functions. Okay, so that's the analytic result, and you also mesh with all known data at weak and strong coupling. Okay, now I have like 7 minutes or something like that. So let me speak about this more recent, so it's independent now topic, more recent results about ABJ theory. So ABJ, like a little bit mysterious one, because it's very similar to ABJM and perhaps is too similar, but however it has two couplings. So you have two Chern-Simons terms with different SYMs, and you can build two 't Hooft couplings out of that. And so for the case, somehow lambda 1, lambda 2, it was well studied and like, you know, aspects of it from integrability point of view. And for lambdas non-equal, there is still probably a question whether it's integrable or not. And so probably like Sergei is already preparing his equation, or rather a comment that it's not integrable. But let's be positive, right, and assume it is integrable and see what will happen. So if we assume it's integrable, first let me recall the integrability construction for ABJM. So it's basically very similar to n equals 4. Okay, there's just the group is different, so you'll find different number of p's and q's, and that's probably discussed on the poster of Diego and Andrea. So the only new, so not the only, but one of the new ingredients is that the position of the branch points is now parameterized in a non-trivial way in terms of the coupling. And the way to fix it is to do comparison with localization, which deals directly with the action, which parameterized by lambda, and integrability always deals with h, which is a mysterious parameter. And what we find with Grisha is that just by observing a structure of the result in integrability, given by some elliptic integral corresponding like to some cuts, so there are two cuts and some integrability result, and mapping it to the localization result, which also has two cuts. Where is the? Okay, So also has two cuts. By just making an assumption that there is a Möbius transformation which connects those two, you'll find this map from H to kappa, where kappa is known from the matrix model explicitly. So, no, it's not explicitly, but implicitly. Right? So then you can, you do, and somehow this simple assumption reproduces all the predictions, and even it recently got confirmed by direct string theory calculation. Okay, so now our assumption is ABJ is also integrable, and because we just want to be positive. However, we tried hard with Fedor and Andrea to deform the spectral curve, but it seems to be too rigid and it doesn't allow for extra parameters. So the assumption is that probably it's the same quantum spectral curve. The only thing we have to do is to reparameterize the coupling differently. And this is indeed what happens at V-coupling. So now, however, this structure of cuts in the matrix model is a bit funny. So it has, it is like that. So you don't see immediately any symmetry of the branch points. But still you can try to play the same game, and you'll find that H is parameterized in terms of branch points in this way. Okay, where the branch points are known in terms of lambda 1, lambda 2, just standard. So those who were on the previous week, they will immediately reproduce this lambda 1, lambda 2 in terms of the algebraic curve data. Okay, so this is our conjecture. Now what are the tests? So first, actually, it's even non-trivial that this H is real, because you see this A's and B's are completely crazy, on the complex planes and some almost random positions. However, so it was analyzed that some reality properties were analyzed in this paper. And if you rewrite this result in terms of some parameters which are more suitable for reality in terms of this U which is real, we'll find that exactly this is real, and furthermore U is also bigger than 1, which is quite nice. Then at V-coupling, of course, it matches all the perturbative data, and then you can also compare at this partial V-coupling limit when only one of the lambdas goes to 0, and this matches also some recent results and also some old conjectures. And furthermore, at strong coupling, you see almost no difference in terms of the most natural coupling. The only difference appears at this term, and which is exponentially suppressed, and this probably is something expected. And Valentina kind of promised to compute this first instanton correction, if I understood her correctly. I'm not sure. Yes? Yeah. So, okay, thank you. So that's one of the tests. And finally, it's also highly expected that this H should be invariant under some kind of Seinberg duality. What? Seinberg, okay. But Seinberg-like, so it's Seinberg, right? So we can call for simplicity Seinberg. Okay. So I hope this part is not recorded, actually. Okay. So what happens? So first, it's not completely clear that it will work, because you expect that if you change couplings, all your branch points go around the complex plane and so on. But what happens actually, we did this numerically, this test, is that the branch points somehow map to each other. So what happens is that this blue one, it goes around the origin, and then the blue and red exchange their places. So you have two groups, and they interchange, and one goes around. And so the one which goes around, it also picks some pole at the origin, which gives rise to this one. And because it goes around the red curve, it also gives you double the contribution of another cut. And this completely explains this duality, but otherwise the branch points are exactly at the same positions. So the H itself remains invariant. Okay, that's the mechanism how this duality works here. Okay, so you can try to prove it analytically, but Okay, that's obvious. Right? So, okay, just one formula in the remaining 1 minute. So just another result, which so we extended our previous analysis of BFK regime to like non-zero conformal spin, which is just S2, and we also understood how to make both charges S1 and S2, those charges in ADS5, how to make them non-integer. So in terms of a quantum spectral curve, you can analytically continue in both, in S1 and in S2, which is quite funny simultaneously. And then we also found very easily that there is a BPS time point for n equals 1 at the origin. Okay, I'm finishing. And then you can do the slope type of calculation, which gives this exact result valid to all loops, which gives like a slope of intercept as a function of n at all orders in the coupling. Okay, and so there is some mystery about reciprocity, but if you're interested, we can discuss it separately. Okay, so these are some random conclusions. Don't take them too seriously. So thank you. Well, as I said, Fourier of a wave function is itself because it's self-dual. So it's equally complicated or equally simple.
But is there any physical understanding about that relation?
And why it's self-dual?
Not the relation between two.
The Millin transform, you mean?
No, I mean the relation between the wave function and the wave function.
Yeah, which is Millin transform, right? So, yeah, so I don't know. No, I don't have any intuition. So this parameter of wave function, apparently it has some physical meaning, right? It's really a momenta of some diagrams. So it's not as simply related as like in what Amit said, where it's almost exactly the same. Here somehow we have to do Millin transform. So I don't know. But Millin transform is essentially, roughly speaking, like Fourier, and since it's self-dual, I don't know. So it's like by dimensions it's the same, but still there is some non-trivial structure in between.
So I remember last IGST last year, we promised the zero model to solve the strong coupling systematically. Do we have some analysis?
So in a sense, I was scooped, but I'm glad too, by Bainek, who analyzed, by Hegedus, who analyzed the strong coupling from the numerics and made some like guesses for the fit of the coefficients. So there are some partial results about strong coupling expansion. So that's still an open question, but there are some directions to proceed.
So you showcased many interesting applications of the quantum spectral curve, or this 564, this 463.
Yeah.
Yesterday we also had many nice talks about this 362. Is the quantum spectral curve possible to formulate in this case?
So as you know, like next year there will be this workshop in Florence, right? So we have to probably wait until then before we close this problem, right? Yeah. Yes.
We have two momentum carry nodes in ADA model.
Yes.
We put H1 to one node, H2 in another node. And why do you think it fails?
Why what?
You said this QSC is too rigid to admit any generalization information. So why if I do
No, at the level of the bit ansatz, you can do many things, right? But at the level of the quantum spectral curve, it's already quite restricted with the kind of things you can do. Because as I said, basically Q system is fixed. The only thing you can modify is the gluing conditions, but then it's very rigid because it should be aftermorphism of the QQ relations. So it's basically there is only a discrete freedom. You can deform it continuously. So you can think about like different types of cuts or stuff like that, but it's really hard then to close the QQ system if you have two types of cuts.
Other questions? Okay, so let's thank Nikolay again for the presentation.